Okay, yeah. Cool. So yeah, reboot whenever it gets stuck. So we're going to talk about active loads. And okay, the first type of active load devices we're going to do common source with active diode load. So what this means is, and some of you have seen this circuit, I think, before. We have our input amplifier, say M1. And then we bias it and add a small signal voltage. And then we have our output. And so this is the load dot. This M2 presents essentially an active load device to the amplifying stage or transimpedance stage M1. As with any sort of amplifier analysis that we've done so far, we can sort of do it in stages and assume that we're first looking at M1 and then figuring out what the transconductance is of the amplifier, and then we multiply that with the total load that the amplifier sees. So just in terms of getting things started, what do people think is R up? R up is the resistance that we would test into the source of this M2. Okay, so that's a good start. So we're saying it's diode connected, so it must be sort of 1 over GM2. The body is also at ground. So there is another thing we need to add to this GM2. Yes, plus GMB2. What else? There's something we usually neglect, but we're not going to neglect it at first. So in parallel with RO2. Okay, so that would be our resistance looking up into the source of M2. And then our R out total will be R up in parallel with what? RO1, right? Okay. So if we do VO over VI, we have the transconductance, which is how much in this case? Yes, it's negative GM1. That's for this transistor. And then times the total resistance. So it's minus GM1, and then we're going to write this as 1 over GM2 plus GM B2 in parallel with RO1 in parallel with RO2. So now we can say, well, this 1 over GM plus GMB2 is definitely much smaller than the 2 ROs. So this is approximately minus GM1 over GM2 plus GMB2. And in situations where GMB2 is 0, let's say if I have a process where I can afford to connect the body to dual triple well process where I can connect the body to the source, I can eliminate GMB2 and I get something that has a pretty nicely defined gain. It's not big, but is actually just because the same current flows through both devices. It's essentially just the ratio of geometries, right? So that's a pretty neat feature to have, so that it's supply independent and to the first order, and also threshold voltage independent. So for this topology, there are some conditions for the DC operating point that we're going to look at right now. What is the regime in which M2 works? Okay, so M2 is in saturation. That's where we want it to be, but what's the condition for the output voltage so that M2 is in saturation? If the output is equal to VDD, is M2 in saturation? No, it's in what region? Cutoff, right? So for M2 to be in saturation, where do you need to be? Yeah. So VO is to be less than VDD minus VTH. And this also is kind of the VTH, the body affected VTH, right? So it's a little bit larger. So M1, we obviously want it in saturation because that's our amplifier. Right? That's the device that has to provide gain. And for this device to be in saturation, what are the conditions? What does V in have to be? Yeah. So that condition tells us that it's not in cutoff, right? But once VI is greater than VTH, what does the V out have to be? Okay, so VO has to be greater than VI minus VTH, which is? Yes, which is V overdrive, right? Yeah, so the output has to be greater than the overdrive, which tells you that this guy can swing between VOV on one side and VTH on another side, right? So the useful range in which I can move is this. On one hand, it can go as low as the VOV of the M1, and then as high up as the VTH less than VDD from M2. So that's kind of the useful range of this amplifier. Okay. There's another type of the active load that has more gain and has the lowest swing, because on the other one we couldn't pull all the way up to VDD or even close because VTH is a pretty large drop, especially in modern processes. So with this topology, so with this topology, we can now swing larger, but let's first take a look at the small signal. So what is the total R out on this topology? RO1 in parallel with RO2, that's right. Because if we just look up, then all of this is gone, right? And the only thing that remains is RO2. Right? And so the VO over VI is minus GM1 times R out. Okay. The interesting thing here is you can say that this is essential. If these two are sized the right way, this is approximately some RO. So if you look at these two variables, GM2 is proportional to the square of the drain current, square root. And then R0 is proportional to what? Yeah. So if you look at the product, is proportional to 1 over square root of ID. So in contrast, in bipolars, what do we have? Okay, so GM is proportional to IC and R0. So from here, then GM R0 is roughly constant, right? So roughly independent of the R. The range of gains we can get in bipolars from GM R0, we sort of already mentioned, was around thousands. Here, in this type of single stage, we can get maybe 5 to 100, depending on the technology node. Okay. But we have this capability that through biasing and sizing of these two, we can kind of affect the gain. If you want a higher gain here, what would you do? We're not using resistors. How could we change the topology? I give you 3 more transistors. How would you get higher gain? Okay, it's good, yeah. So you would go one diode, and this is like one way. We've done several ways how we would do it, right? Right? So I have now a P cascode as the current mirror. So that gives me roughly what are out. Okay, it's proportional, but there's another factor, right? Anybody remember? Roughly. For all these cascoded devices, what's the output resistance? And then looking down, we have similar thing, right? So then our total gain would be what? Well, minus GM times this, right, which is GM RO square, approximately over 2, if these two are the same, right? Okay. So now we can get this topology is getting us approximately a square of the gains that we halved, but I mean this doesn't really matter. It's a small factor. It's approximately squaring the kind of gain we can achieve from the single stage. Of course, the penalty we pay is that here I can get this device in saturation if I have the VOV, right? This device, we've analyzed it as a current mirror. What is the voltage? What's the highest voltage that VO can go up to before this one goes out of saturation? Yeah, so this one, well, I'm talking about this device. Yeah, there's a VOV here as well, right? So this is kind of the largest swing I can get out of an amplifier, but I don't have much gain. And then with cascades, if we do this one over here is not going to give us the smallest overhead because it's not a Such cascade, right? So we're going to have to pay a threshold penalty. But at the bottom, if you adjust the VB, we could get away with 2 VOV, right? So if I change the current mirror topology, I can get by having something that's 2 VOV from the rail and then another 2 VOV from the bottom. So that will be my useful swing. Okay. So just in terms of analyzing these kinds of things, sometimes it's when you're asked to draw something like a VO as a function of Vin, which you had in homework a few homeworks ago. Usually, it's interesting to look at the ID versus V out, and so our bottom device would have a whole bunch of curves that all correspond to a certain VGS that we're applying. And VGS will be V in, right? And then we have another curve, which is our load device curve. And that one would go something like this. So this one over here will be our VGS2. So for example, in the previous simple mirror thing, if I have a certain current here, ID or IREF, oops. If I have RF here, then that current will set this VGS. And that will essentially determine what is this curve that I'm writing on. So this point over here would be my IREF or ID. Let's call it ID. Because I may have a multiplication ratio in the current mirror or something. But it's essentially the current that is set by I2. So now, by starting from this point and moving through these points, I'm traversing kind of the V out versus V in space, because I'm moving on the V out axis, but I'm also crossing the lines where the V in is changing. Okay. So for example, here, if I start from here where V out equals VDD, so if V out equals VDD, then I'm in cutoff region, right? Because my ID is 0. Okay. And I stay there till when? Till my V in goes to what value? VTH, right? So my V in gets to VTH. And then I start, then I'm, my V out is at VDD. My V in is at VTH. I have all the conditions to be in saturation. So then I start immediately off in saturation at the bottom device, which is M1. And so I start pulling down. And then I'm going down, going along these curves until I hit the VOV point. when my other device, meaning M1, goes into triode region. Okay, so this is sort of a quick run through the active loads. We're going to take a look at now how we can use these active loads in biases, which is kind of what we covered in the last time. And the basic concept is that we'll have two blocks that we learned so far. So we're going to have current source at the bottom. And that source is going to give us I out. And we're going to use then a current mirror to map that I out back into I in. It's kind of like a chicken and egg thing. Because if I had a current source, you know, we usually had to provide some input to it, some reference from which you're going to be generating. So it's either VB or something on a drop on a resistor, and that gives us the I out. Well, in this case, I sort of say, well, assume I have some input, right? So I have some input current, and I will produce, as the current source, I'll produce the I out. And then if I mirror that back, then I get it back as my reference. But I'm using sort of as a reference something that doesn't really exist at the very beginning, right? So intuitively, if I had a 0 here and I propagate it out and 0 maps back, that's also a valid value. So that's a little bit of a problem. And in fact, if you take a look at this type of arrangement, if we draw the I out versus I in for this type of circuit, we have two curves that we're kind of trying to match. One is a straight transfer line, which is our current mirror. Right, current mirror has some multiplication ratio between input and output, and that will be the slope of this curve. But it's directly mapping whatever's into the output. And then I have this current source characteristic, which is usually mapping some reference into voltage, etc., and so or mapping voltage back into current. So it will look something like this. Okay. Okay. So if you look at this curve, there are sort of 2 points here that are kind of the solutions or the stable points for this system. One is where everything is 0, and this is usually actually a stable point. Since normally, if there were no leakage currents, this would be an unstable point because you would, once you're hooked up to supply, you would sort of stretch some voltages around and that will turn things on. But because of the leakage currents, it will still provide kind of a low loop gain, and as we will see later when we analyze feedback, it will sort of, it actually is the positive feedback loop around this is, the loop gain is less than 1, so it will actually stay in this point, kind of nicely stabilized, which is what you don't want to. You want to be in this, oops, I don't know why it did that, so we'll just draw it again. You want to be sort of in this point over here because that is where all the currents are non-zero. So let's take a look at some circuits, how we can realize this. We can, as a current source, we can use the source that we derived a few lectures ago. So this was kind of the one that was not as sensitive to the supply voltage, right? because it was VGS1 over R. So it wasn't dependent on the supply. And then what you have at the top is, okay, I don't know why this is happening, but okay. What you have on the top is just a normal current mirror. Okay, and so then you can take this node over here and push it into another transistor, and then you can take the I bias from here. If you really want to get another bias, so this is, let's say, 2, you could also take it from this point over here. Because the same current is being reflected in both. Okay, now notice what we did here was, so this was our I.O. This is I.in. I.in on this diode gets converted into a voltage. So that voltage is the square root of the current, right? And then that voltage, which is a square root of the current, gets mapped on R and generates I.O., right? That's why this curve looks like this. Okay. So let's take a look at this circuit over here. If I move I.O. high, my I.in is also going to increase, right? Because this diode, VGS becomes greater, so I.in becomes greater. If I.in is greater, then this VGS is going to be higher. So then voltage across this resistor is going to be higher. And therefore, I.O. is going to be higher. So there is a positive feedback loop. But it's stable as loop gain is less than 1. So we'll see when we kind of do the analysis in follow-on lectures, when we go into feedback, we'll see that if you sort of apply the little test here on current, you would see that the total loop gain is actually, it's positive feedback, but it's less than 1. And therefore, it's not going to completely accelerate and slam you into one of the rails or accelerate the current indefinitely. Okay. But the point that there's positive feedback and then there's this extra solution over here means that you would have to have a startup circuit. So if you were to build this for real, you would have to have a circuit that will kind of make sure that you end up in this point as you put your supply on. And so I'll give you an example of a startup circuit. So if we go and redraw this thing just real quick. Okay. I want to have a circuit that will essentially get this node, turn this diode on, and be able to start getting some current through this resistor over here. Once that happens, then everything will sort of turn on its own. So we'll have a circuit that looks kind of like this. It's a simple inverter. And then I have another transistor here. And then I'll use this, okay, maybe on the other side. So I'm connecting it to basically this voltage over here. And let's label these guys, M7, M8 and M9. I'm going to label this M1. So what's happening here is that in my initial state, let's say if I end up in this state where there's no current flowing, right? So there's no current flowing through this resistor. Oh, sorry. This is this voltage, which is across the resistor, is driving the gate. So if there is no current, then this voltage here is 0. That pulls this input low. If the input is low, then this transistor will be off. And M8 will, with its gate low, will pull up this node all the way high to VDD. That will turn M9 on. So M9 will pull this voltage down. And as it pulls that voltage, that's actually this voltage. As it pulls that voltage down, there will be now VGS here that is greater than threshold voltage across, and you're going to start conducting some current. As that current is non-zero, it will start this R, it will start developing some voltage here. And as the current now sort of goes into the second stable point, right, because it's going to go here, get developed here, and get developed the right value across this, when this value achieves IO times R, this is going to be sized in such a way that at that point, M7 turns on. And, well, M8 is not going to actually completely turn off. So M7 will turn on and pull this voltage down. Okay. Because this is not going all the way to VDD, M8 is still on. So M7 has to be much, much bigger than M8, right? So what's happening is that when I achieve some VGS for M7, M7 better be so big that when it gets out of cutoff, it immediately pulls down M8. Okay, so with this ratioing at the stable point, M9 is turned off, and then this node is let go to basically be established with whatever the value was for this particular thing. Okay, let me give you a few other circuit examples. So this is for VBE self-biased. Again, we have a current mirror at the top. And now we're just doing the current source a little bit differently. So in this case, we're going to have our VGS source here. Sorry. But instead of doing the VGS reference, I'm going to do the PNP reference. Okay, so in this case, as long as these transistors are same, I'm dropping same VGS over here. So I cancel that impact, and I only have this VEB dropped across R. So this is VEB1. Okay. So my I out is VEB1 over R. Right. So another example, something like this. Again, same trick with the current mirror. That kind of stays the same. And then down here, okay, who can tell me what this does? So over here on the left, we had the VEB reference circuit, right? So I'm just producing the current that's proportional to the base emitter voltage. In this one over here, what am I doing? Why do I have two transistors that are PNP? One and n means this guy's n times larger. So we're doing last lecture some tricks about different sizing of PNPs. Yeah, the leakage current, the IS would be kind of larger in one versus the other, right? But what was the key when we used the two PNPs? So here I have my I naught is essentially going to be determined by the difference in the two VBEs, right? Ah, sorry, to confuse you. Okay. There is R here, okay? So the current through here is VEB1 minus VEB2 over R. And what did we say for the difference in, whenever we have a difference in base emitter voltages, what does that end up being? There is a log, but it's a log of a constant. But the proportionality changes. Instead of being proportional to VBE, you're now proportional to something else. That's also very useful. So you're proportional, just think in terms of VEB. VT ln of IC1 over IS1 minus VT ln IC2 over IS2, right? So that's VT ln of the ratio of the collector currents times ratio of the leakage currents, right? And so because same current is flowing here unless I ratio these devices as well, but if I'm not, the same current, then this is 1. And I can provide, N is the ratio of the leakage currents because just the areas of the emitters are different. Right, so then the difference is just log of N. But the proportionality is to the thermal voltage, right? And in all this temperature-independent biasing, we wanted to have something that is proportional to the thermal voltage because it has a positive slope, and then something that's proportional to VBE, which has a negative slope, and then we can kind of multiply those two together and achieve sort of a zero slope at some target temperature, right? So this would be an example of a circuit where you generate the current that is now proportional to VT ln something, right? Okay. That's kind of all that we're going to do on the biasing and circuits. The rest is a little bit for homework this week. But I want to start with doing some of the bipolars next like 10 minutes or so. I'll do a quick run-up of differential pairs with bipolar transistors, just because you have some of those examples in the lab. And then we're going to jump into the MOSFETs. So if you take a look at the bipolar amplifier, I can put two sort of common emitter type stages in this configuration, where I have I tail, and then I have Q1 and Q2. I have VI1 and VI2. And then I'm trying to figure out what is the transfer function from input to the output currents, right? I have I1 here and I2 here. So the first thing that I can do is look at what's happening between VI1 and VI2. So it's kind of like a KVL. So VI1 minus VBE1 equals, or let's just do it the whole loop, plus VBE2 minus VI2 equals 0. This means VI1 minus VI2 equals VBE1 minus VBE2. Now, VBEs, we know, we just did this, are VTLN of IC1 over IS1, and this one will be VTLN IC2 over IS2. Okay. So our input voltage, the difference of the input voltages will be VT log of IC1 over IC2 times IS2 over IS1. If these two transistors are the same, then IS currents will be the same. Right? So the area of the emitters is going to be the same. So this is gone. And the ratio of currents will be equal to the exponential of, we're going to call this VI differential over VT. So the ratio of the currents will be exponentially dependent on the difference of the input voltages. That means, like, for very small changes in the input voltages, the currents will swing drastically around, right? But if I look at this IC1 and IC2, by KCL, because I have this I tail over here, I'm sort of tying the emitter currents of these two transistors in so that their sum has to be some constant, right? So I emitter 1 plus I emitter 2 has to be equal to I tail. And so from here, right, so alpha f was this like 0.99 factor, right? It was 1 over 1 plus beta. Okay, so this is our sum. And now, since I have the ratio and I have a sum, I can actually express both IC1 as over 1 plus e to the VID over VT, and then IC2 as this. Right. So what this means is, just depending on the sign of the difference, I'll have one of the two quantities go exponentially down to 0, or another one slam up to the I tail. Right. This is, of course, valid only until all the current is moved into one branch, right? After all the current, so if I'm increasing my VID as positive, after I've moved all the current from Q2 to Q1, meaning after I2 equals 0, then this no longer applies, right? Because further movements, then I tail flows completely through Q1. So its VBE is actually just VT log of I tail alpha times I tail over IS, right? So at that point, game over, okay? So this only applies until both are in forward active region, right? So we can say Q1, Q2 are in forward active region for this. Okay, so let's draw that line a little bit. So if we do IC1 and 2, and then we'll do the VID. The top will be alpha F times I tail. And this will be .5 times that. And what will happen, as we said, is if VID is very large, one of the two sides will saturate. So you'll hit alpha F I tail here, and then as you're coming down, bad drawing. This is 0. And then another one come this way and hit 0. If you look at kind of at what point you really slam kind of all the way, because this is exponential tail, right, as we're doing it, approximately at 3 VT. So if VID is 3 VT or minus 3 VT, you've kind of moved all the current from one branch to another. So you can assume that you're no longer having kind of this swing of current. And so you can say that VID input range will be plus minus 3 VT. So that's the range in which the output currents are still reacting to the input voltage. After that, the one output current is 0, another one is whatever the tail is. However you keep increasing VID, it's not going to help you. You're not going to see it at the output, right? So you're interested in this range because this is the range in which your input voltage can still manifest itself in the output currents. And if you add some proper resistances there or loads, it will also show up as the output voltage. Outside of this range, nothing. So input range. Now, does anybody have an idea how we can stretch this input range a little bit? Make it larger. As I'm changing my VID, I just have to divert it so that most of VID is dropped now somewhere else and not across the base emitter, right? Because the current reacts exponentially to the base emitter voltage. So what can I add to this diff pair to kind of drop the voltage somewhere without dropping it on the base emitter? I can add a resistor where? You mean here? Well, here it's only going to start pushing collector down. But it's not going to be, I mean, it's related to the VID, right? But it's not directly dropping VID across it, right? If I have a very large VID, I need to spend it somewhere so that only a fraction of VID gets dropped across VBE, right? So take a look at this equation, right? This is the equation that determines what amount of VID gets dropped on the VBEs, right? Can I insert something there to sort of absorb all the VID? Resistor in the base, well, that's fine, but the base current is very small, right? So where's the current large? Emitter. Okay, great. Okay, now we're getting somewhere. Okay, so emitter, you get something like this. Right. So now my VID is VBE1 minus VBE2, and then plus oops. So if you try to solve this, okay, you're going to see that it's not that easy because VBE1 and VBE2 contain this factor, I-tail, right? And so you'll end up with this sort of a transcendental equation because you have a log and then a linear term outside. And if you sort of write a numeric program, you'll be able to solve it. But the bottom line is that what this will do is on the characteristics that we talked about just in a moment, instead of just doing this, very close to 3VT, you'll get something that looks more like this. It's a milder transition. And this stretch is by I-tail RE. Okay. So you're kind of absorbing the shock on each side by I-tail RE. And you can sort of know that just intuitively that at the point where this guy is no longer conducting current, all I-tail is going through RE. Right? So at that point, VID is